Okay, so we are going to talk about pyramids, in particular image pyramids. So you know this is a pyramid, and it is where? This is where? In Egypt. So how many people have seen this, have been to Egyptian pyramid? You? One? Anybody else? How many people are from Egypt? You are from Egypt? Okay. So how many of you actually want to see this pyramid? And why don't you go there? I mean, must Okay, so these are more pictures of these pyramids. So Egyptian pyramid, there are total 138 pyramids, and they keep finding these pyramids, and this is up to 2008. And as you know, most of these pyramids were built as a tombs for the pharaohs, who were the kings and emperors. And there are different locations these pyramids are found, and these are the places. The earliest pyramid which were built was long time ago, 2630 BC, about 4,000 or 5,000 years ago. And they were kind of designed by this architect, that was his name, Imhotep. And there were lots of people worked on it, and there's no correct estimate, but it is, from few thousand to 100,000. And the most famous pyramids are the Giza pyramid, as you know. And these are, among the 7 wonders of ancient world. So, these pyramids are interesting geometrical artifact, and people used to build these, long time ago. So we are going to talk about image pyramids, and these are very useful for representing images. And pyramid, as you saw, the Egyptian pyramid, or these image pyramids basically are going to be built by multiple copies of same image, but a different resolution. Okay? So each level of pyramid is 1/4 of the previous level. It will be reduced by half in X and Y direction. And lowest level is the highest resolution, and then the highest level is of the lowest resolution. Okay? So this is a pyramid. So we start with say 512 by 512 image. We get 256 by 256, 164 by 164, 128 by 128, and 64 by 64, and like that. We keep doing. You end up with 8 by 8, 4 by 4, 2 by 2, and 1 by 1. So if you put these things on the top of each other, it becomes like a pyramid. Okay? So that's why its name is pyramid, and this is a pyramid of real image. It looks like that. Of course, it's not a triangular base, but it's a rectangle. So these pyramids are useful, and this is another example. And we are going to talk about 2 special kind of pyramids. One is called Gaussian pyramid. Others called Laplacian pyramid. And again, as we have been talking about in this course, that Gaussian will play a very important role. We will, keep revisiting Gaussian thing, many different contexts. So this is the pyramid, and as you see that, this is the full resolution, and we have these different lower resolution and so on, and this is, kind of showing that if you show these at the same size, then this is 512 by 512, but this is 8 by 8, and you don't see much details. Resolution is reduced, even though we have stretched it out to see the same size. The other pyramid we are going to talk about is Laplacian pyramid. Again, we are going to kind of stay with Laplacian, Laplacian Gaussian, and Gaussian, and so on. There are these few concepts which we'll be using, repeatedly in this course. So as you see that Laplacian pyramid is is different from the Gaussian pyramid. Gaussian pyramid was like an image, but this looks like, edges. These are the points where there is some change happening, and we'll show you some examples of that. Again, these are different levels: 512, 256, 128, and so on. Keep going up to 8 by 8. So one important method for detecting humans or objects is called deformable part model, or DPM, which is very popular, works pretty well, and where you can detect a human. This is like a human part, and these are the parts of the human. And in order to do that, you will have to build a pyramid like this. There's a pyramid, and we'll find the features in this pyramid, which is called HOG, histogram gradient orientation. Actually, one of the exercise there, and will actually help you to understand that well. At each point, find the gradient direction, and then look at the small neighborhood and find a histogram of gradient direction. It's called HOG. It's a very popular feature, works very well. So the main point is that the person or any object, an airplane, bicycle, and all these objects you are interested in the image, they can appear at a different size depending on how far they are from the camera, depending on the size of those objects. So you want to be able to detect those at any scale. So in order to do that, then if you have to build a pyramid, and you'd see, well, is it here, is it here, is it here? So there'll be some scale where it will be visible. So that's the idea of using the pyramid, because a priori we don't know what's the size of the human it appears, and we want to be able to detect that. Okay, so it's a very important tool which is used a lot in different things. So in today's lecture, we're going to talk about how to build Gaussian and Laplacian pyramid, and in that context we will discuss two operations. One is called reduce operation, other is called expand operation. So reduce operation essentially will reduce the resolution of an image by half in x and y direction. Expand will increase by half, increase by twice as much. So there are many applications of the pyramids, and in particular we will discuss the application of Laplacian pyramid in image compression and in image compositing. And actually this will be a program you will write to be able to test your understanding of the pyramids. So I'm going to cover this from this paper which was published by Peter Bird and Ted Edelson, called Laplacian Pyramid as a Compact Image Code. And it is highly cited paper. It's a pretty old paper. And these are the two authors. Can anybody tell which one is Ted Edelson and which one is Peter Bird? Just guess. Right is Peter Bird, and left is Ted Edelson. How did you decide that?
Just by the name on the box.
Yeah, that's pretty good. It's correct. So Peter Bird is right, and Ted Edelson's left. And Peter Bird retired, I think, last year or year before. He was at Sarnoff Research Lab, or SRI, it's now called. It used to be called RCA Labs in Princeton, New Jersey. He was a PhD from University of Maryland under Rosenfeld. As I told you, Rosenfeld was one of the pioneers of image processing, vision. And Ted Edelson still is a professor at MIT. And he and Peter Bird, at that time, they used to work at Sarnoff. So these are the authors of this paper. And let's talk about the Gaussian pyramids reduce operation. Okay, so again we are going to do the convolution. We are going to build the pyramid using convolution or correlation, as we have been talking about. So what we are going to do, we will take the GL minus 1, which is the Gaussian pyramid, say at level L minus 1. From there we are going to get GL, which is a Gaussian pyramid at level L, and the way we are going to do it is basically convolution. We take the values, multiply with the mask, and it's a two-dimensional mask, and we'll get this at pixel ij. We'll get these around ij. We'll look at small neighborhood and then get these weights. So this is the 5x5 window, because as you see the loop is from -2 to 2, so -2, -1, 0, 1, 2 for in the x and y direction, or m and n direction. So this is level L, and just for simplification we will represent this. GL is reduced of GL -1, and this is convolution that we'll take a pixel, get a 3x3 or 5x4 neighborhood. We have a mask, we apply pixel by pixel, we replace here, and we'll keep doing that for all the pixels, which we have been talking about for a long time. Okay, so now just to look at here, that there is one difference compared to what you have learned in the convolution or correlation. And what is the difference here? In this formula, there's one difference. And what is that difference? Yes.
The 2i.
2i and 2j. See, in other one just I and j. So there's no twice. And that is the idea, that we are reducing by 2. And that's why we have 2i, 2j. So when we'll have loops, so we will skip one. Okay? So that's good. And so now we can take that for 2D convolution, we can look at 1D convolution to make it easy to explain. So here I'm just looking at GLI. Loop is from -2 to 2. Again, it's a mask, and this is the L-1 level, and 2i plus m. So what we can do, we can expand the summation. Let's say I is equal to 2. So we can take, say, m is equal to -2, so it'll become w hat -2, gl -1. So I is 2 is 4, and m is -2, so it'll be 4 -2. Then I'm going to take m is equal to -1, so it'll become w hat -1, and here is 4, and m is -1, and then I'll take the m is equal to 0, and then this will become the 4, because this is 0, then 2 multiplied by 2 is 1, and like that I can expand this thing for the 5 terms from -2 to 2. Okay, it's very simple. So I can simplify. This will become 4 minus 2 is 2, and 4 minus 1 is 3, and all this thing. So that is essentially I'm doing in the convolution of applying this mask to the GL -1 to get GL. And this is a 1D case. So if you look at the example here, so say let's say this is G0, so I have 9 pixels. Then from here I get G1, then I get G2. So to get this pixel here in this level, so I'm going to look at these 5 pixels. This one, this one, this one, and multiply with these masks, weights. Sum it up, we get here. Similarly, to get this one, then I'm going to look at the 5 below it, and up again have the corresponding masks, weights, multiply this with that, and sum it up like that. So same way to get this one, I'm going to look at this, and these 5 here, and like that. So that's the way I'm going to build a pyramid, different levels of pyramid in one dimension. Very simple, as we have been talking about. Yeah.
How about the edges?
Yeah, so edges will be same as we talk about. You can truncate, you can do all those kind of things. Yes.
Why would you have masks in there? If you're just reducing, you probably want the average of everybody.
Yeah. So the question is that the mask, what should be the weight? So if you want to do average, then the weight will be 1/5, 1/5, 1/5. If you do weighted averaging, then you will have Gaussian mask.
But why would you want the weighted average if you're reducing?
No, I mean, you are reducing the resolution, but you want to get a smooth version of your image at next level. Otherwise, you will have problem which is called the aliasing and sampling problem. So it's always we need to have the smoothing and then subsampling, smoothing and subsampling, like that. Okay. That is what the reduce operation is.
I have a question.
Yeah.
When we producing the pyramid, why when we reduce, why don't we just sampling the even column or even row? It's much simpler, I think.
Yeah, of course. I mean, lots of things in life are simpler, but they're not good. See, so the reason we want to, because we cannot subsample, because we are going to smooth and apply the Gaussian filter to those. Then if we sample, then we will get a meaningful reduce operation, as compared to when you sample like that, it will have a problem. Because see, what we are going to do, we are going to remove some, when we smooth, we are going to remove some frequencies. I don't want to get more into Fourier domain and lots of image processing related thing. I want to limit your discussion to computer vision and computer science. But that's the main idea, that it's not a good idea to just sample. You're going to lose information. You need to smooth, so that you want to get rid of those frequencies, and then subsample, and that will give you better version. And you can try it out. See, when we are going to build the program you are going to do about compositing, you will notice the difference.
So it is possible the smoothing first and a simple sampling in the second step. Is it okay?
That's what we are going to do. Yeah. That's exactly what we are going to do. Smoothing, apply filter, and then sample. And apply filter, then sample. So the way we are explained here, that we are going to, the sampling will be just your program, because 2i, 2j is doing sampling. So what we are going to do here is that these weights are essentially smoothing. They are applying those weights of which these are actually Gaussian masks. So I'm going to talk about that. Okay. Is that fine? Yeah.
You said we're going to do it in 2 steps. We're going to smooth first and then move.
Yeah. I mean, so that step is just we'll take every other pixel. We'll skip every other pixel.
We'll be smoothing even pixels we're going to drop in the second stage?
Yeah, I mean, so what we are going to do, see here, so we want to find pixel number 2, yes? Mm-hmm. We'll come down, we get these pixels. Then we want to find pixel number 3, and then we like that, very simple. Okay, so now there's another operation, which is the expand operation, which is very similar, but here you see there's upon 2. Okay, so this will expand. And again, we have the mask, and the same, this is a Gaussian level L, which has been expanded n minus 1 time, and this will give you Gaussian level L, which has been expanded n times. And this is the same thing, that's a 5 by 5 mask, and this is the way we are going to represent this. So again, we can take this one-dimensional case to simplify and expand this. So this is if I is equal 4, then we can take a value of this minus 2 to 2. So if this is minus 2, it's become like that, and I is 4, and minus 2 is 2 upon 2, then we can take P is equal to minus 1, and expand that, and P is equal to 0, and like that, P is equal to 1, P is equal to 2. So you'll get these terms, you just expand the way the formula is. Now there's one thing here, that we have 4 plus 1 upon 2, which is 5 upon 2, which is 2.5, which is not integer. In the image we have their integer value. So similarly here we have 3 upon 2, which is 1.5. So and this is okay, because 2 upon 2 is 1. So we are going to get rid of those. Okay, so those numbers which are not integer we would not use. And so then this will reduce to this. We'll get from here 4 plus 2 upon 2 is 3, we get rid of this. The 4 upon 2 is 2. Get this one, we get rid of this, and we get this one. 4 minus 2 upon 2 is 1. So this is actually we have only 3 terms when you do expand as compared to 5 terms when we're doing reduce. Now we are going to talk about what should be the weights, and these weights will be here we will have a, and this will be B and B, so it'll be a symmetric weights, and we're going to talk about that. And so we can also take the, say, pixel number 3, and we expand this. Again, P goes from -2 to 2, and the same thing. And here you will see that this will be removed, and this will be removed, and this will be removed because they are not integer. So we'll actually have only 2 terms, the 2 and 1. And again, this will be B and B. So that's the expand operation. That's the way we are defining, and we are going to do that. So if you look at expand operation in terms of the picture, so this is the level L, and we're going to expand one time with the GL1, and we have these pixels, as you see, 5, and we're going to come up with like this. So now we can number these 0, 1, 2, 3, 4, and as you saw here, that if we have the pixel, the expand operation means of 4, then we can use these terms, which are according to the formula there, and when it's 2, we have these terms, this one, and this one. So this is C, this is C and B, and when it is so when it's a 4, so we have to use the 1, 2, and 3. When it is which is shown here, this was what we expanded, the 3, 2, 1, and these are the weights, and that's what we have here. Now if we want to do this for 3, which is this one, and we have 2 terms, which is the 2 and 1 here, and which is shown here, this one and this one. So that's the way to visualize that, how we are going to apply this GL to GL expanded one time. Yeah.
In the picture, I'm reading C from 1 to 4 and 3 to 4. Is that supposed to be an A? Or is it just...
No, so see we want to get this one, yes?
Yeah.
So this should be C, this should be C, and this should be A.
Can I see the formula again?
Yeah, sure.
Yeah, I know.
Here.
But okay, no.
Okay. So that's what we expanded, as you saw here.
Yeah.
Okay. So same way, that was for 4, and we can do for 3. And 3 we have using the 2, which is 3 here, 2 and 1, like that. And you can do for any one of those.
And why do for the 3, they both have the weight B for 2 and 4?
Yeah, I mean, so that's what we ended up with. See, that's what we got it here. So we're going to talk about, this is W hat -1 and W hat 1. So because we wanted to make it symmetric, so it has to be like that.
Okay.
Yeah. Yes.
Can you go back to the picture? I'm curious, if we're trying to expand this, it looks like we're smoothing out, I mean, there's a weight in there, but we're smoothing out values between pixel 1 and 2 and 3 on the top. For 4, since we're trying to recover as much information, why are we smoothing it out? Shouldn't we just use 2 directly for 4? 2 from G1 going directly into 4, and G1, 1, 1.
No, I mean, so see, the idea is that we are going to apply the more weight to the central pixel. That's a Gaussian thing. Right. And the weights on the left and the right, they will reduce. So it is the weighted average of the one from the top to bottom, or when we're doing the other way, it will be like from bottom to top.
I understand what we're doing, but
Yeah.
I'm just saying it doesn't feel like it's right because we're trying to recover information. The pixel in the center is going to have is going to be much more significant than 1 and 3, considering they're.
Which one are you talking about? 4?
The 2 going to 4 is going to have. I think it's going to have all the information for that.
Okay, just hold on. So you want to talk about 4? How we get 4? Yes?
No.
Or 3?
Well, with 3, I can understand it's a.
Yeah, you understand.
Between 1
Yeah,
and
so you understand 3 how to get.
Yeah.
It's okay. You understand 4?
For 2, I'm just saying the weight, the C weights.
2?
They should be.
Which one? 2
yeah.
here?
4, I guess.
That's what I'm asking. Yeah, 4.
The weights, it's getting weights from G1, C, A, and C, right?
Mm-hmm.
I don't think if we're trying, because it's effectively a form of smoothing, right? If we're using neighborhood pixels from the top, it shouldn't be just. We should be using just A, I think, for 4.
No, that's the idea. See that we don't want to, when we smooth, we don't want to use the pixel just itself. We want to change the pixel based on some neighborhood. That's what we have been talking about. That one way will be say, well, we have a pixel, just use that value. But we say, well, that pixel can randomly be noisy. That something happen.
Mm-hmm.
So that's the whole idea of smoothing, is that you take a small neighborhood around that pixel and get a kind of weighted averaging. And of course, the central pixel you want to give a higher weight than the other pixel.
So it's only for noise, I guess.
Yeah, I mean that's the whole idea. Smoothing and noise, all this whole idea is that we don't want to rely the pixel itself. We want to rely pixel around the neighborhood, and we want to make sure that pixel at that center place has more importance compared to other ones, but we want to consider the other also. Okay? Any other question? Yes.
The length of the next one.
Huh?
2 times the length of the next.
Yeah.
It is 2 times the original.
Yeah, I mean roughly 2 times, because see you have this even, odd, and all those things. So, but that's the idea. You want to roughly get twice as much, and depending on also mass size, you will miss, as she said, miss on the side and so on. Okay. Any other question? Yeah.
So if we reduce from one level and go one level up, and then again expand back
Mm-hmm.
to that level, can we replicate the exact thing, or it's coming from?
Yeah, we're going to talk about that. Yeah. Okay. Yeah.
I think it's not precise to omit the atom whose index is not integer. I think if it's not integer, we can try to make the integration of the 2 pixels. For example, 2.5. I make the integration of the 2 and the 3, and use the 5 the weight of 0.5. Yes.
Yeah. So that's a good point. So what he's saying that right now we just cut rid of those, and other way will be we do interpolation. That we get the value here, and find that. And what we are just talking about, very simple way to do this, and still it's pretty good. It will do what we want. But yeah, I mean one can do that if you want to do more precisely. Any other question? Okay, so let's move forward. Then so now this is our convolution mask. Okay, so this is a 5. Of mass size 5, and this is our 0, 1, 2, and -1, -2. So right now, we don't know what should be that mask. We just apply, we define it, say it's the convolution of the, level below and above, and that's the way we're going to do. Now, what we are going to do, we are going to put these constraints and actually derive what should be the weights, and they will turn out to be actually Gaussian, so which is pretty interesting. So what first we want to do, because we are going to deal with the 2-dimensional images, we want to make it separable. As we have talked about, separability is always very good, because it will reduce the computation from n squared to 2n, and which is nice. Okay, so which means that we want to do 1-dimensional convolution on each row, and then 1-dimensional convolution on the column at the result, and this is the same thing as a 2-dimensional convolution. And we also want to make it symmetric, because it makes sense that the weight we assign to the left and the light should be similar. So symmetric, to be fair, equal opportunity, So we want to be fair. And then using these 2 constraints, so which means that, well, if the center pixel is A, next pixel B, then and next pixel C, then these has to be B, C. That's the, so far we have these weights, So it is symmetric, and we are defining right now one-dimensional mass. So now another constraint we will have that we want to sum these weights to 1, because it's easy when you sum to 1, then you take an image which is between 0 to 55, you will end up with image 255 after filtering. Okay, so which means that we want to get the A plus 2B plus 2C is equal to 1, because there are 2 B's, 2 C's, and 1 A. Other thing we want to do, which is very important, that all the nodes at a given level must contribute the same total weight to the nodes at the next higher level. Okay, so we are going to explain this, and then we'll come back to that. Okay, so here is this picture again, and we have these levels, and as we said, in order to get this, we are going to use these 5 pixels, and in order to get this, we are going to use these 5 pixels. In order to get this, we are going to use 5 pixels. Okay, and these are the weights. For example, this one we'll have A, B, and C, and B, C for this pixel. These are the 5 weights: A, B from here, C from here, B from here, C from here. Okay, for this pixel, A from here, and B from here, C from here. For this pixels, A from here, B from here, C from here. So that's the way it's going to work. So now we have to look at that what kind of pixels we have at the lower level. So one is this pixel, which is contributing A, C, C. So it's contributing A plus 2C. There's another pixel which is contributing B, B, which is 2B. And that's it. There will be 2 kinds of pixel actually. If you look at all these, that's what they are doing. Okay, so so therefore we will have this constraint which will say A plus 2C, which is A plus 2C is this kind of pixel, and B plus B is 2B, which is this kind of pixel. The contribution from this pixel is this much, contribution from this pixel this much. They should be equal, because every pixel contribute equally to the next level. That's a constraint. Okay, so when we put that constraint here, and that's what we have, A plus 2C is equal to 2B, and we have A plus 2B plus 2C is equal to 1. So as you see now, we can actually simplify this. How? Because A plus 2C is 2B, so 2B plus 2B is 4B is equal to 1, which means B is equal to 1 upon 4. So right now we know the value of B, 1 upon 4, but using this constraint. It is symmetric, it is summed to 1, and each pixel should contribute same weight to the next level. Okay, so that's what we can do, and then once we know the B, then we can find the value of the C, and we can then determine the value. It will be only determined by value of the A. Okay, so suppose let's find the value of C. So we know that we have 2B minus A from here is equal to 2C, so C will become half of 2B minus A, and C will become 1/4 minus A upon 2. So therefore, if we define A, we know C, B is always fixed 1/4, then we have the whole mask, but there are 5 values. Okay, we have ABC, and then we have other side also BC, and we came up with this as a constraint which we can satisfy, that they should sum to 1, they should be symmetric, and they should contribute equally. The nodes from the lower level to the higher level, they should contribute equally. So that's what we have. So therefore this mass will be determined by A, and these weights are W of 0 is A, W of minus 1 is B, W of minus 2 is C, and they are symmetric, so W of minus 1, W of 1 is same, W of minus 2 and W of 2 is same. So that's it. Now what will happen that if we select A is equal to 0.4, then the mask will look like Gaussian. If you select A is equal to 0.5, then it will look like a triangular, and you can see that. So this is a triangular mask because B is always 1 upon 4, and then we have A is equal to 0.5, it will look like that. But when we change to the other value, A is equal to 0.4, then it will look like a Gaussian bell-shaped curve. So typically we'll use this one. Okay, so that is our mask. We define it using these constraints, and it look like Gaussian, and you can apply Gaussian if you like. So that is the mask, and you can look at Gaussian as a function as we have been talking about. Then you can take different value of x here, and these are the values, and then you can plot. Looks like that. As you see, this is similar to this one, and it is separable. That's the way we have defined that we can apply the mask on each row and skipping every other pixel. Suppose this is 8, so we'll get 4. This is 8, we'll get 4, and so on. And then apply the same mask along each column. Again, skip. So from 8 we'll get 4. So we get 8 by 8 to 4 by 4. And that will be the next level of the image. It's pretty simple, very, very nice, intuitive. Okay, so the algorithm then is very simple. Apply 1D mask to alternate pixels along each row of image. So this is where we are doing sampling. Basically, it's very simple. We're just taking alternate rows, alternate pixel along that row. Then apply 1D mask to each pixel along alternate columns of resultant image from previous step, and that's it. So if you look at this image, these are the different levels of Gaussian pyramid. Okay. Now there's interesting other pyramid which is called Laplacian pyramid, and which is from this French mathematician Laplacian. Came from Laplace, French mathematician Pierre-Simon Laplace, lived in 1749 to 1827, and he has contributed a lot to mathematics and astronomy, and he was considered French Newton. Every country used to have equivalent Newton. As you heard, Leibniz was a Newton of Germany, and this guy was a Newton of the France. Now, interesting thing about this guy is that he came up with lots of interesting ideas: Laplacian, Laplace transform, celestial mechanics, spherical harmonics, and so on. But interesting thing is about his wedding, and he actually married on March 15, 1788, at age of 39. He was pretty in a way old, but he married with this young lady who was only 18 and a half years old, from a good family. Okay, so that's the human aspect of this guy. Okay, so let's look at how we can get the Laplacian pyramids. So I want to make it interesting for you guys. So okay, Laplacian pyramids. So that at least you will remember that this guy married with young wife. So then you can recall the Laplacian, how did those work. Okay, so now Laplacian pyramid is similar to detected edges, and it's actually Laplacian of Gaussian. We'll have similar things here. And most of the pixel will be 0 in that pyramid, and it can be used for image compression. And the idea is very simple, that we will take the level 2 of Gaussian pyramid, G2 is Gaussian pyramid level 2, expand it, then subtract that from G1. G1 minus expand G2. okay? Because as you know, G2 is half the resolution of the G2 is half the resolution of G1, so we'll expand it to make it the same resolution and then subtract pixel by pixel. That will become the first level of Laplacian. Yes?
So you said the expand is the Gaussian expand that we did before.
Yeah, so I mean expand operation is that to take an image, you will expand twice as much. Now, the original, we will take a original image, say we make a Gaussian, Gaussian pyramid of that. The lowest level of that we will call G1, the next level is G2, G3, G4, G5. And G1 is the original image, but we'll just use the notation just a G1, or sometimes we use G0. Then we will do the reduce operation on that. It will become half the resolution, we'll call that G2, and then G3, G4. So it's, at the lowest level it's the original image, but when you go to higher level it's a Gaussian, because whenever we do the reduce, then we have to apply Gaussian. And whenever you do expand, we have to again apply Gaussian. So what it's saying, you take the level 2, and that can be that G2 means that the original image is the G1, which we haven't done anything, and then build the Gaussian pyramid, so G1, G2, G3, G4. Now from Gaussian pyramid we are going to build Laplacian pyramid. The way we are going to do it, take the G2, which is 1 times reduce of G1, expand it, so now it will be same resolution as the G1, and subtract from G1, it will become Laplacian, L1. Okay? So same way you will do the L2. Now we'll take G3, expand it, subtract from G2, become L2, and so on. So L3 will become G3, expand G4, subtract it. So it looks like that. So on the top is showing the Gaussian pyramid. We have just changed the size so that it's the same size, but the resolution is small. Keep going smaller. So what we have done here is the original image, then the second level of Gaussian expanded, we subtract that, we get this L1. Then we take this one and take the next level and subtract it and get this level of Laplacian, and this, subtract this, and so on, keep going. So this is a Laplacian pyramid, this is a Gaussian pyramid, and as you see that in the Laplacian pyramid most of the edges are highlighted. So this is what Laplacian pyramid is doing, and you remember the Laplacian of Gaussian was essentially doing that for detecting edges. So this is,
It's a difference of Gaussian, right?
Yeah, so this is also a difference of Gaussian. We're going to talk about that. That's another relationship from the SIFT and so on. But this right now, what we are doing is the Gaussian pyramid, and we are subtracting. So in a way, you can say, you apply one Gaussian, another Gaussian, and subtract, and that's what we are subtracting, getting the Laplacian. So all these concepts are linked, they are related, but you need to understand fully to appreciate what you're doing. Because that's the beauty of science, that at the end, the facts are very few. There are very few things which you need to know. Then you can keep building on your knowledge to then relate these things, and that you can really enjoy that what you are looking at. Because science you cannot memorize, like it's not a history, it's not a fiction, it's a fact. And that you need to really fully understand that what the concept is and how it relates to other things and you can fill in these things. So all the lectures we have so far, all these should be very integrated now. That we have an image, we have a filter, we have a Gaussian, we have a weighted average, we have derivative, gradient, magnitude, orientation, Laplacian, all they are coming together. Harris corner, again there are derivatives. So it's interesting. Okay, so so now what we are going to talk about that how we can use the Laplacian pyramid. Yes?
The edges which appear on the image.
Mm-hmm.
Are these edges essentially in any way related to the edges we lost due to smoothing? You know, when we reduce, we smooth the image.
Mm-hmm.
So we would have lost some kind of information there. So are these images which appear here in any way related to those which we have lost?
I mean, what do you mean by loss? Like, see when you smooth, you can blur the image, and you are subtracting also. So you're looking at a kind of difference or kind of gradient.
Yeah. Basically, what images due to blurring, there's some kind of distortion which is there.
Yeah, I mean, see, one way to look at that, you are filtering. So you are removing the some frequency information in image. If you look at the frequency domain, so one is a low pass filter that we are only allowing the low frequency, and other is a high pass filter that we are allowing only high frequency. So at the edges there's a high frequency because there's a change, there are lots of changes. So Laplacian Gaussian in a way is a high pass, so it will filter out, it will give you only those which are high changing, which are the edges, So that's kind of, you can relate to that way. Okay, any other question? Okay, so now interesting thing is that you can use Laplacian pyramid to do image compression, and which is very nice. So the idea is that you have an image and you want to compress it. Compress means you want to use as few bits as possible per pixel, so that you have fewer bits, like JPEG compression, and there are lots of other compression. So what we are going to do, we will compute a Gaussian pyramid of image we want to compress, and this is a Gaussian pyramid, and this is the original image, and these are different levels of pyramid. Then from there we will compute the Laplacian pyramid, and as we talked about, Laplacian pyramid is like this. And then what we are going to do is we will code the Laplacian pyramid using lossless coding, and what's going to happen that Laplacian pyramid will have fewer non-zero pixels. Most of the pixels will be zero, and it will require fewer bits, and that's where the compression will come. But then we will be able to recover the original image G1 from the Laplacian pyramid. That's the idea. Okay, so it's very nice. So the decoding will happen that we are given the Laplacian pyramid. It was coded to save bits. Then we will decode it, and then from Laplacian pyramid we'll compute the Gaussian pyramid. Okay, because from Gaussian we computed Laplacian by subtracting. Now we'll do other way, and we should be able to do it. So the way we are going to do it, the last level L4 is G4, okay, of the Gaussian. Then we are going to take the G4 and expand G4, and then add L3, we will get G3. Because this is the same thing, we just subtract. That's the way we generate it. Remember this thing? We just move on the other side, it will become plus. Yes? Because G1 will become expand G2 plus L1. G2 will, this will become L2 plus expand G3 and so on. This is what I'm doing. Yes?
So as part of the decoding of the Laplacian is the whole pyramid. We'll keep all the levels.
Yeah, we'll code separately each level, and we will then decode this. Then we get this level of Laplacian. We'll decode this. We'll get this level. So we get that. Okay. So we do that, and then the last one is G1, which is our original image. That's it. So we can reconstruct. We can get the original image back. Okay. So that's the way we did it. Remember, here we have G1 was the original image, and we generated the G2, G3, G4 Laplacian pyramid. From that, we generated L1, L2, L3, L4 Laplacian pyramid. Laplacian pyramid we coded. We caught at the other end, we got Laplacian pyramid. And we decoded. From that, we have all the levels of Laplacian. From that, we computed the Gaussian pyramid. And at the end, the last one is the reconstruct image, which is very good. Yeah.
Is this compression mode used anywhere?
Yeah, I mean, so this is more like conceptual thing, and this was pretty old method. And if you remember the wavelets, these days JPEG 2000 is a pretty popular compression instead of JPEG, and some of these ideas worked from here, the wavelets. Wavelet transform is similar thing, much more complex, where the Gaussian, it's not just Gaussian, but oriented Gaussian in different directions and so on. So now this is your Laplacian pyramid. Now the reason why is it compressing? Why is going to save bits? And the reason is shown here, that we have an image like this, Lilina image. Now if you look at the histogram of this image, it looks like that. Okay, so it has all kinds of gray levels here, and so we can look at what is called entropy of this image, and which will give us idea how much information this has and how many bits we require to represent this. And this, if you look at the minimum number of bits we need to represent this image with this histogram is 7.6 bits per pixel. Each pixel is 8-bit, so this as it is, we cannot compress that much because it has all kinds of gray levels as you see here. And that is a problem. This is a kind of exception. This image is, has this kind of distribution. Now, the reason the Laplacian pyramid works well, so these are the different levels of Laplacian pyramid. And if you look at the next level, this level of pyramid, the entropy here is 4.4, which means we need only 4.4 bits per pixel to represent this image, because most of the pixels are 0. If you look at histogram, it is center is 0, most of the pixels are 0. Okay. Similarly, this is the next level, again centered 0, 0, and so on. So this is what is saving us bits, because we are subtracting and most of the pixels become 0, and we are able to save bits. Now in addition to that, we are going to do quantization, because all the compression actually quantize. And when we do the quantization, then this will become even better. Now instead of 4.4 bits, we need 0.77 bits per pixel for the first level. For second level, 1.9, 3.3, and so on. So that way, we are going to save lots of bits. And then this is example. One on the left is original image. One on the right is the compressed image. It's very difficult to distinguish. For the top one, we can do 1.58 bits per pixel, which is very good, instead of 7.7. For this one, we can even do 0.73 using the Laplacian pyramid. Okay, so that is a very nice application of Laplacian pyramid. Yeah.
In the previous slide, what was the last column and what happened there?
This one? Yeah. So what we did the quantization. So see the quantization, as you know, that your homework is and the exam and so on are 100 points. Yes. To represent any number between 0 and 100, how many bits you need? 7 bits, yes? Now what I do, take the 100 and quantize it to grades A, B, C, D, yes? How many bits you need? 2. So that's called quantization. So I'm reducing the number of possible values to these quanta, and that's what essentially, and somehow the human system, the vision system is not sensitive to that. If you quantize it, it's okay, and all these compression techniques do that. Okay, so that's what we have here. Okay, so let's talk about last thing. So as I've been telling you that how you combine apple with orange. Okay, and this will be one program you will actually write. So let's say, I have, I show you this, and you say this is artificial, this really doesn't make sense. There's no fruit like this, you will have. And when I show you this, you say, well, I want to eat this. On this side apple, this side orange, it's real. It looks very real. But it is synthetically generated using the Laplacian pyramid. And you're going to do that. Okay? And it's very easy to do it. So the algorithm will be that you will generate the Laplacian pyramid LO of orange image, and you will generate the Laplacian pyramid LA of apple image, and you know how to do it. I just explained to you. Then you generate a new pyramid called LC, which is a combined pyramid, Laplacian pyramid, and that will have half of the nodes or pixels from the apple and other half from the orange, and then there will be middle pixels for which you will find the average between apple and orange. Okay, so now you have pyramid LC, and then you reconstruct from LC the original image as we reconstructed the Gaussian image, the last level, and that will look like that. So all this discussion is from a very nice paper which I showed you earlier by Ted Edelson and Peter Bird, 1983. So it's about 20 years old, and I also describe all this thing in my book, section 4.4, and this will be the next assignment which you will do, how to combine these two images.